This video is going to cover free fall, and we're going to define what that means, but basically it is something accelerating due to gravity. Now, we're going to look at some plots, and we're going to look at how we actually do with it mathematically, but really this is about problem solving. So this is again a case where there's a model you're going to use a lot, so you need to understand when it's valid and what simplifications we'll be making. The other thing about this is we're going to be working a lot with this later on. So the next section will actually look at inclined planes, which is related to free fall, and when we move into two-dimensional motion, we'll do projectile motion, which is also related to free fall. So while this in itself isn't necessarily that complicated, this video will be shorter than normal. We will be coming back to this frequently later. So first thing is to just know the definition, which is that free fall is when we're only worried about gravity. Now something that's a little tricky right now is we're not talking about forces, but when I say gravity only, I mean the only force we're worried about is gravity. So if you're familiar with the idea of forces, that's how you can think about this. If not, don't worry, we'll cover forces in a couple of weeks. So gravity is the only thing we need to worry about. In particular, what we're not worried about is air resistance. Now, if you think about a situation in your everyday life, if you're just standing up at whatever height you happen to be, and from one hand you drop a piece of paper, and from the other hand you perhaps drop an eraser, the eraser seems to get to the ground faster, it gets there first, and the paper kind of drifts back and forth. And what's going on there is that air resistance is preventing the paper from just falling down with the same acceleration that the eraser does. But what we can do is if we remove the air, not from the room you're in obviously, but for instance from like a vacuum tank, or perhaps on the moon where this experiment was done, and you drop two objects, for instance an apple and a feather, as these fall they actually stay at the same height. So they're accelerating downwards at the same acceleration. Why is this? Well, as we're going to talk about, everything on Earth has the same acceleration as long as air resistance is negligible. So we really have to talk about forces before we can define what this means. But the good news is right now in this class, because we really only have free fall as the situation we can work with, you shouldn't need to consider air resistance. So sometimes I'm going to explicitly tell you that air resistance is negligible. Other times you should be able to just think about situations where it is or is not true. So dropping a dense object like a rock, it works out that usually then you don't need to worry about air resistance. A piece of paper, a feather, things like that, you usually do need to worry about air resistance. So that's just something to think about. Now, the other thing to be a little bit careful of is free fall. You might think about that as, well, fall is right in the name. However, we can actually have different initial heights and different speeds. So free fall can totally cover the situation where, for instance, you have maybe some grass and you have some sort of rocket that you're going to launch upwards. I don't know what rockets look like, but maybe it looks like that. And we would worry about the situation after the engine has cut off and it's traveling upwards at some initial velocity, and we maybe would consider just starting from this initial height. So even though it's not falling, we would still call this free fall at this point, as long as there's no, as you can see here, as long as we're not worried about the, as long as we don't have the engine on. So free fall is any situation where you only have the acceleration due to gravity. It's okay if you have an object that's actually traveling upwards, as long as the engine isn't actively on. So that's the thing to think about here. And again, we'll talk a little more about things like this. There's actually a lot of neat videos you can see online, including one taken on the moon, where once when we sent an astronaut to the moon, he dropped a hammer and a feather and saw that in fact they did hit at the same time. So again, the model that we're dealing with here, the simplification, is that we only need to worry about the acceleration due to gravity. Now, what is that? We actually call this acceleration, we refer to a constant, g, and this is lowercase g. One thing to be careful about is there's a gravitational constant that's capital G. That's a different constant. That's actually a universal constant. This g is only true for Earth. So you might see this written as g sub Earth. In general, almost all of the physics we do in this class takes place on Earth, so you don't normally need to worry about this. However, we might see some situations where we're dealing with situations on other planets. So for instance, Mars or Saturn or imaginary planets. The moon is another situation where we can think about free fall. The moon is technically not a planet, but it still has gravity. And because the gravity there is different than on Earth, you would have a different value for g. So this is specifically for Earth. If we're working with a different location, like a planet or a moon, we would have a different value. Now, something that is important to state, again, depending on your previous knowledge, you might understand where this is coming from. This is valid on the surface and what I would call normal heights, including mountains or being on an airplane. If, for instance, you wanted to talk about how the moon orbits the Earth, well, maybe then we can't use this anymore. So once you're talking about astronomical distances, this value isn't really applicable anymore. Again, we're not going to do that in here, and that's where you have to start thinking about the universal law of gravity. But in the situation where we're on Earth, and that includes even on an airplane, we can just focus on this. Note that it does have units of meters per second squared, and as we're going to see, that's because this is an acceleration. Now, something that's going to be pretty important for how you both communicate your work and how you are careful to do your work correctly is that this constant should be positive. This is the value, the magnitude of acceleration on the Earth. We're going to talk next about the direction, and frequently in equations, minus signs are going to show up. But one thing that's really important is that you don't put a minus sign in this constant, that the minus sign appears in the equation itself because that's talking about the direction of the acceleration. So please keep the constant positive and put the minus signs in the equations where that deals with direction.